and welcome to our, I suppose, first in-person seminar for this fall semester. And it is my pleasure to introduce to you our speaker today, Professor Aaron Smith from the University of Ottawa in Canada. Aaron is an associate professor there at the Department of Mathematics and Statistics. And before joining Ottawa, he received his PhD firstly in mathematics from Stanford University under Diapanis, where he worked, according to him, mainly on mixing times of Markov chains. And then he did two postdocs, one in applied math in Brown University, and then also in stat at Harvard University. And according to him, again, he learned some things about stat and applied math there. And then he also worked, I think, for 1 year at the federal government in Canada before joining Ottawa as a faculty. His main research interests are in applied probability and theory of MCMC methods. And needless to say, he has done lots of excellent work in all these areas over all these years. And today he's going to tell us about some of his recent interesting work on reconstruction of linear embeddings on graphons. So please join me in welcoming Aaron.
Well, thanks very much. It's really nice to be giving a talk in person, and exciting to have a big group of statisticians around to talk to. So yeah, so most of my work is sort of on Markov chain Monte Carlo, or at least most of my published work that's related to statistics. But I sort of figure that the people who are interested in that here already know what I have to say. And it's sort of a forbidding topic for people who aren't already into it. It sort of always ends up feeling a little bit technical. So if I would talk about a sort of smaller project that's more related to my applied work, which I think has a lot more sort of open questions that at least I'm interested in, and which are maybe not so difficult, or at least I don't know that they're difficult. So I'm going to be talking about this sort of word soup, statistical seriation, reconstruction of linear embeddings of graphons. If you know some of those words, great. If you don't know those words, that's fine. I'm going to start off with a couple of pictures. Okay, before the pictures of the data, pictures of my co-authors. So I'm going to be talking about a couple of papers, two of which are papers that I'm a co-author on. The first is a paper with Jeanette. She introduced me to this problem many years ago. And the second is Minatik. He was one of my master's students at Ottawa a few years ago. He's now a PhD student at Mila, and a really interesting guy to talk to as well. Okay, so what's the problem? So I'm sort of a math person most of the time, so there's going to be a lot of math in the back half of the talk, but I at least want to start off talking about a problem that's sort of a substantive problem, and that motivated all of the statistics stuff. And so the problem that got all of this seriation started was a paper that's actually quite old, from 1899, by an archaeologist named Petrie. And so he was interested in the following problem. He goes into a bunch of archaeological sites. In his case, he was digging up graves when he was interested in this paper. And he finds all of these different types of pottery. And I'm not sure how easy it is to see here, but you can see sort of there's pottery up at the top where there's red for sort of most of the pottery, and then a little bit of black at the top. And then somehow that changes a little bit. Then you get a different color down here, different colors, drawings starting appearing, and then some other stuff happens down here. Okay, I'm not an archaeologist, but anyways, even I can see that things change over time. And what he was interested in trying to figure out was how old these different types of pottery were. So which potteries came first, which potteries came later, how long did they last for, all of that sort of stuff. Okay, so no statistics, but is the problem somewhat clear, right? You get to see all of these different shards, they look different, you want to try to put them in order. And sometimes that problem is easy, right? Like everybody's seen, sometimes you have grave sites and they have dates on them, so life is good, right? Somebody tells you the answer. Sometimes you recover pottery from, say, sunken ships. Somebody's written down somewhere else where the same ship went down, so the data is available. But in this particular case, there were no numbers lying around, and also sort of the usual other tools involving looking at the dirt, they also weren't available. And so it seems a little bit hopeless. But he came up with this sort of cute idea, and I'm going to call this Petrie's algorithm, although the algorithm involves him getting down on the floor with pieces of paper. And the algorithm was as follows. For every individual one of the graves, so say 30, he's going to write down one strip of paper. And on that strip of paper, he's going to write down all of the different types of pots that he sees in that grave. So this requires some judgment, right? But anyways, he's going to enumerate the types of pots, and he's going to list down which ones are in each one. And he's going to do that for every one of the graves. And so he has all of these long strips of paper. He's going to put them on the floor, and he's going to try to rearrange the strips of paper in the following, according to the following rough criterion. if you look at any one type of pot, for example, this one here, the time from which it first appears to the last time it appears should be as short as possible. So that's his criterion. The column for every pot should be as short as possible. Why is that sort of a reasonable-ish thing to be thinking of? I'm not an archaeologist. I don't want to claim this is exactly the right thing to do. The idea there is that you have pots which so before some period of time, right? The pot doesn't exist. Nobody's figured out how to make it, or nobody's interested in that. The pot exists. It's very, very popular, so you see it as much as possible, and then it goes out of existence, right? So if you're able to date them at all, that's sort of the story that you have to have in the back of your mind. So assuming that the problem is solvable, this is sort of a reasonable criterion to have. Now, maybe it's wrong, right? But anyways, that's the problem that he was interested in. He thought that that was reasonable. Okay, so he did this, and it worked pretty well. It worked well enough that people do this all the time. But it's not really an algorithm, right? He's just sitting down and trying. It's not really statistics. There's no statistical model. And actually, there's not really an objective function, right? You want to make each of these columns as short as possible, but it's not clear that you can do that in a conflict-free way, right? Maybe making one column shorter makes another column longer. How do you balance those? You just sort of looked at it, right? So, okay, we're going to try to move towards that, from that problem towards something that looks a little bit more like mathematics. So the first thing that you can do, of course, is to try to make it look like mathematical notation. So there are a couple of reasonable ways that you can do that. I'm going to choose one that's sort of the easiest. I'm going to make a graph just with single edges, and the graph is going to be as follows. The vertices of the graph, V, are going to be the list of graves. And I'm going to draw an edge between two vertices if there exists a type of pottery that it shows up in both graves. So the idea is if the types of potteries are sort of localized in time, then I'm mostly drawing edges between graves that were dug at similar-ish times. And the hope is that if I do this for very, very many graves, I can actually figure out an ordering of all of the graves in time. Okay, that's sort of the prayer. Now, I think it's very natural to look at it and go like, is that really a reasonable way to encode the data? I think the answer is actually sort of no, right? So in particular, here, if I have one grave that has 10 types of pottery 1 and one example of pottery 2, and another grave that has one example of pottery 1 and 10 examples of pottery 2, those both look the same in that embedding. That's clearly a little unreasonable, but okay, it makes the problem description a little bit easier. I also don't really care about the graves. I care about the types of pottery. So maybe I should be looking at the dual graph where the vertices are styles of pottery, and I draw an edge between styles if they co-occur in a grave. Right, that's sort of more what I care about. Yes, maybe there are actually some problems with doing that, but it's something that one can try. I'm mostly going to ignore that and just stick to this graph formalization. But also, I'm saying this first of all because it's a natural question to ask, and also just to sort of assert that a lot of the stuff that I'm saying more or less is going to work either way. So the details, those sorts of details don't matter too much. Okay, great. So where are we? We haven't done any math yet. We have this sort of data set of plots. We have this thing that Petrie did. He wrote a paper. People seem to like it. It's not really an algorithm. And we can write it down in modern notation. So the next thing we want to do is we want to write down sort of a reasonable objective function. We want to write down a reasonable algorithm. And we want to say some statistics about it. This was 120 years ago. Those things didn't all happen at the same time. And it turns out the first thing that people worked on is writing down sort of the easiest version of the problem. So writing down the problem where you get a clear algorithm, but without any sort of thinking about the objective function or about the statistics. So what does that actually look like? So this person named Robinson was the person who started working on it. And his sort of idea was, he doesn't want to think about what the objective function is supposed to be. He just says, what's sort of the easiest possible version of the problem, one where I don't have to think about the objective function at all. And that easiest version of the problem, that's one where you can simultaneously make all of the columns short at the same time. There's no conflict at all. Right? So that way you don't have to think about how these things are going to go. There's no statistics. You just find the one best thing. Everybody can agree on it. So, okay, what does that actually look like? He wrote down a criterion, which I've copied down up here, which is the criterion that you need for that to be true. Okay, so the graph has this nice property. If there exists a reordering sigma of the edges so that, well, this thing happens. What is this thing? What the thing happens is when you rearrange the edges, and you look at the sequences of ones along any row in the adjacency matrix, those ones have to occur in exactly one interval. And when you look at the ones in the columns of the adjacency matrix, those also have to occur in exactly one interval. Okay, so that property there is the same thing as this consecutive one property that I just wrote down, all the ones appear in an interval. So what do those adjacency matrices look like? Well, if I look at this picture, I can imagine that every pixel corresponds to the entry in my adjacency matrix. If I colored all of the ones dark red and all of the zeros these other colors, that's sort of what these adjacency matrices look like. So they have a bunch of entries that are sort of close to the diagonal, but you can sort of wobble in and out in all sorts of different ways. Okay. So this is the sort of the nice version. So this is maybe a good time to pause and say, okay, is the nice version reasonably clear? At least, not that it's easy, but that there's no objective function to worry about, and that the definition is sort of okay. We're going to make things messier pretty soon. Okay. Great. So that was the problem that Robinson was interested in. And it turns out that actually there are these very, very clever algorithms that people can come up with. So people wrote sort of a dozen papers or so tackling this nice version of the problem, and then ended up with these super fast algorithms. There's one of them that takes 3n steps to run, guaranteed. Really, that's a 3 in front of the n. So it's a very, very fast thing. And they give exactly the right answer for Robinson matrices. So if the matrix has this nice property, then you're going to find the sigma really, really, really fast. But if you think about that for a second, you should become instantly quite suspicious. An adjacency matrix has n squared entries. I'm only touching 3n of them at most. That's if I don't really touch anybody. So whatever assumptions I'm making had better be really, really strong for that to be even plausible. And so that's actually true. So if you run these sorts of super fast algorithms on actual data sets, like from Petrie, you can just get chaos, right? It depends a lot on initializations, right? So bad stuff can happen. So these algorithms are cute. I've never seen anybody use them for a real data analysis problem. What people tend to use are these sort of more robust algorithms, which seem in practice to be sort of not very sensitive to noise. So I'll just sort of say for now what one of those algorithms is, and it's based on something called a spectral embedding. So if anybody's seen spectral clustering or PCA or whatever, great, you've seen it already, but I'll say it now anyways, just to set some notation. So the idea is you have a graph, it has an adjacency matrix A. You do a little bit of tweaking to the adjacency matrix to get something called a Laplacian matrix delta. Everything's symmetric, so this thing has nice, has real eigenvalues. You order the eigenvectors according to the eigenvalues, and you take the second one. Why the second one? Okay, well, you stare at it for a second, and the first one doesn't work. And so that has a name. I'm not going to call it the second one anymore. It's called the Fiedler eigenvector. And so what you do is the following: every point I gets mapped to the real number phi of I. Okay? So that's a thing you can do, right? You can write it down in R or Python or whatever in 2 seconds, and that's something that maps points to that maps the vertices to points. And if you've seen sort of the stochastic block model problems, this is actually what you do for the size 2 stochastic block model as well. So this is not new to this problem. And what do you do once you have that embedding? You do the obvious thing. You put all of your points in a row somewhere, and what's your ordering? Your ordering is the ordering given by that embedding, right? So that's written down the formula here, but it's just the first thing that you can think of. And there's a theorem which says that if A is Robinson and isn't sort of hugely degenerate, so it's not like the all zero matrix, then you can recover the unique true ordering by doing that up to reversals. Okay, so this actually works for the original problem, and moreover, it seems to be at least somewhat insensitive to noise. Okay, so that's where we are right now. We have a data set. We have Petrie's approach, which people seem to like. We have this sort of formalization of Robinson, where he writes down the easy versions of the problem. A bunch of people over many years come up with many solutions, some of which seem to be disastrously bad for real data sets, some of which seem to be okay when you draw the pictures. And at this point, we don't have models and we don't have guarantees for actual data sets, but things seems to be sort of okay. And so that leaves sort of the obvious open question. If I do one of these algorithms that people are writing down and I do it for like an actual data set, what can I say about the end result of that procedure? So that's mostly what I'm going to be talking about for the rest of the talk. I'm going to say a little bit about what the probabilistic model is, so I can start talking about statistics. And then I'm going to go through a couple of algorithms and a few results that we have. And I'm always a little bit worried for these sorts of talks that it's just going to look like some huge pot of results that are sort of hard to digest quickly. So I want to spoil things at the beginning and say what my favorite part is, either so you can listen for that part, or even better, so you can tell me that I'm wrong afterwards and that something else is more interesting. So my favorite part was sort of the following. The first thing is we figure out that for a pretty broad collection of these models, not everything, but a pretty broad collection, the spectral clustering technique, the spectral embedding technique works in the sense that you get consistent estimators as the size of your matrix gets big. But it turns out that doing these two-stage procedures actually can't be optimal. So it's not just that the two-stage spectral thing isn't optimal, but actually no two-stage thing in some sense can be optimal. So we come up with another algorithm which is actually much, much better than any of the two-stage things can possibly be. Okay, so that was sort of fun for me. And I think at least a little bit of a surprise. That is, I talked to some people before working on this who told me that, yeah, maybe the math is messy, but the spectral thing is the right thing to do. And it turns out it just really isn't. At least it often isn't. Okay. What's not in the talk, sorry, the data part is done. I had one data set. This stuff gets used all over the place in other situations, in biology, natural language processing, and so on, but all of that's sort of messy. And so for the rest, I'm mostly going to be talking about math and algorithms. Another thing which is often a little confusing, which is why I don't talk about seriation in the title. Seriation, as far as I know, used to be from sort of archaeology and geology, but some statisticians recently have been working on it for another problem that's related to putting things in order. So if you look up statistical seriation on Google, you're going to find a problem that also involves putting things in order, but it's really different. They're related, but the relationship is complicated and the properties are very different. I'm just not going to talk about that at all for now. Happy to talk about it later. Okay, great. So that's all of the setup. Now let's start talking about sort of actual math and probability. So I have to introduce sort of my huge class of random graph models where this data can be coming from, and then talk about what does it mean for sort of these problems to be at all tractable. So the big class of models I'm interested in are these things that are called graphon models. Okay, so if you've done a non-parametric phase, you've probably seen these before, but if not, I'll say what they are. Formally, a graphon is just some function w from the unit square to the unit interval. And to sample from this graphon, what you're going to do is you're going to write down a bunch of latent positions, ui through u1 through un, and a bunch of, well, I don't know what you call these things, uij's, also uniform IID in 0, 1. And you're going to put down an edge if and only if uij is less than or equal to w of uij. What does that have to do with anything? Okay, I'll try to draw a little picture. So let's say I'm looking at a big graph and it has some sort of adjacency matrix, and I'm going to assume that the adjacency matrix is reasonably nice. Actually, I'll say this as a graphon. Okay, graphon is sort of reasonably nice, say 0.9, 0.5, 0.5, 0.9. Okay, something along those lines. This is a graphon, right? For every point in my unit square, I have a value that's between 0 and 1. Okay, I'm going to sample a big graph from this graphon, and then I'm going to write down the adjacency matrix. And if I write down the actual adjacency matrix for my big graph, right, I'm going to have a bunch of ones and zeros, right? 1, 1, 1, mostly ones here with a few zeros, and an even mix here roughly, even mix here roughly, and mostly ones here, a few zeros. Okay, so if I look at them individually, I just get a bunch of ones and zeros. But I can sort of squint, and I can take the average of the adjacency matrix over these little regions. And if I take the average of the adjacency matrix and I make the adjacency matrix big, and I let the size of the balls grow in sort of the right way, then that averaged adjacency matrix is going to converge to this thing here. Okay, so the graphon is sort of a limit of adjacency matrices. Now, I threw a lot of stuff under the rug there. That's not quite true for every graphon in exactly that way, but that's sort of the idea. Okay, and it's really true for this one. Oops, and I seem to have gone backwards. Great. So that's what a graphon is. It's basically this continuous analog for an adjacency matrix. And then I want to say that whatever my graphon model is, it better be a graphon model that's at least sort of tractable, right? So my graphon model in principle might have nothing to do with linear orderings of anything, right? In which case I have no chance of being able to reconstruct anything interesting about the ordering of things, right? But I better have it so that at least the graphon has some notion of linear structure. And so that leads to this definition here. We say that a graphon is Robinson if it satisfies this inequality there. Okay, that's a little bit opaque, just like the original definition is opaque. What does that really mean? It means that if I write down the graphon, I'll call this the thresholded graphon, W sub alpha of xy, is just the indicator function, that W of xy is bigger than alpha. That is, I look at the super level sets, and I look at a graphon from this, a graph sampled from this, that one has to be Robinson. And that has to be true for every alpha, okay? So in other words, this sort of looks like a graph that's Robinson in expectation in some sense, okay? So this is sort of the nice way of saying that, yeah, if you look at sort of missing data, you end up with something that looks like a Robinson graph. Okay, that's the only plausible definition. As soon as you get rid of this, you end up with sort of weird cycle things happening. It becomes very hard to imagine how you could try to reconstruct a linear order. But I won't get into that. So that's the setup. I have these things, these graphon models, which are some big class of random graphs. I've said I'm only interested in these Robinson ones, which are sort of the biggest class of graphs for which I have any hope of being able to recover something, for which it really makes sense to talk about recovering something. And so what do? I do sort of the natural thing. I sample a random graph from my model. I don't know the model, I just know it's in this class. And I know that that model, there exists some true ordering of the latent positions. And I want to try to estimate that true ordering. And these graphs aren't actually Robinson, so I'm not actually going to be able to find the true ordering, right? It's usually not going to be accessible to me. But I'm going to try to find an estimate that's as close as possible. And in particular, I'm going to measure that in things like normalized L1 and normalized L infinity. Okay. So at this point, hopefully it looks like an honest to goodness statistical problem. I have a lot of random variables, I have an objective function, and I'm going to try to measure things. Now, there are a lot of graphons. I don't want you to be thinking about all of them. I think sometimes it's handy to sort of have two examples that you can hold in your hand. So my favorite two examples are these things, the threshold example and the linear example. So if this threshold example is a graphon that looks like this, A here, 0, 0, and this thing has width 2b. That's sort of the easiest possible graphon that looks Robinson. And what's the linear example? It's the same thing, except instead of having a constant value, it sort of goes to 0 as you go further away from the graph, from the diagonal in a linear way. Okay, so those are sort of easy things to keep in mind that I'll try to refer to. I do want to make it really clear that the theorems that we have don't rely on being inside of some sort of parametric family. So all of the theorems are involving like integral conditions and things along those lines, these sort of soft conditions that apply to non-parametric large families of W, but they're a little bit messy to write down anyways. It works for these things and it works for sort of uncountably infinitely many other things as well. And with that out of the way, I can actually write down my theorems in a way that I hope is understandable. So the first is that if you use the existing spectral clustering method, just sort of straight out of the box, you get consistency, and in particular, the L1 error goes to 0 at some rate like n to the minus 1/6. Okay, so it goes to 0, but maybe not very fast. In our two papers, we come up with two sort of cleanup algorithms which do something other than spectral clustering, often with sort of spectral clustering as an input. And those ones are much faster, so they go to 0 at rate n to the minus 1/2, and also the norm gets better. So we go in L infinity instead of L1. And in some sense, just to sort of comment on where things are in the literature, because it's not always so clear when walking through a talk, those are both sort of in some sense expected. That is, it's pretty clear if you look at simulations that spectral clustering more or less works. And if you sort of do the usual central limit style back of the envelope calculations, you should expect the error to go to 0 at something like 1/√n speed. Okay, so that's sort of what you normally expect. And we have sort of a partial converse, which is that if you're going to embed things, if you're going to come up with an ordering that comes from an embedding, that has error that's also bigger than roughly n to the minus 1/2. So we get these sort of, at least up to polylog factors or something matching upper and lower bounds. But we come up with this new voting algorithm, which at least for the threshold example and some other big class of graphons, actually have an error that goes to 0 much faster than that, something like 1/n instead of 1/√n. Okay, so why was that sort of exciting for me? First of all, it's always sort of nice to come up with a new algorithm that's actually genuinely better than some stuff that people used. It was surprising to me, and I think surprising to some other people that we could do that. And then it sort of has this sort of cute thing that happens at the end, which is that somehow people use these two-step procedures where first you embed and then you order. And it turns out that actually ordering is fundamentally easier than embedding. So this is a two-step thing. You're doing a hard thing first in order to do an easy thing, and you end up losing some efficiency when you do that. Okay, so I think I'm sort of halfway through the talk, and at this point I've said everything. So these are the results. And if you don't like math, it's okay. You can go to sleep for 20 minutes or so, and I'll talk a little bit about where these things come from. Okay.
I wonder which item is the latent part.
Oh yeah, sorry, the U's. Yeah, so when we're doing the graphon sampling, what happened was every vertex got a point between 0 and 1. And then you got an edge. It was an edge if and only if Uij, the sort of independent randomness, was less than Wi Uj. So these are those are my latent points. These are sort of dummy variables that we don't try to infer. Yeah. Okay. No, actually, this is a great time to stop for a second because that's all of the actual results, and then the rest is talking about where they come from. Yeah.
Is it easier because when you try to get some intuition, when you try to estimate the latent positions, you're trying to get exactly where you is, whereas in part you only want to know whether one's smaller or larger.
That strikes me as very plausible. So I have a story in my head, but I haven't figured out how to turn it into anything precise yet, where what sort of seems to happen, it's sort of not very surprising that your estimate for UI can sort of wiggle in an interval of size about 1 over root n. And the thing that happens empirically is that my sort of u hat I plus 1, it wiggles sort of the same amount. So you end up getting this sort of correlation that pops up. But turning that into something, I don't have a precise answer. I wish I did. Yeah. Okay, so I'll wander through and sort of go over 4 results and say a little bit about them. So the first 2 were sort of the results that I think were more or less expected by people who worked on this. The spectral embedding works, and you can get something that goes down to 1 over root n, and then the last 2 are ones that were maybe a little bit more surprising. So let's go back to the spectral thing. So I wrote down the spectral algorithm that people write down, so I'm just going to sort of recall it, which is the following. If W is 0 or 1 valued, then the graph sampled from W is actually Robinsonian. And so you can write down the Laplacian, you can take the top eigenvector of the Laplacian, you can use that embedding to order the vertices, and you get the right answer, assuming there is a right answer. And so the natural thing is, well, if G is sort of close to Robinsonian, if W isn't 0, 1 valued, maybe the same thing more or less works. And so I think the first thing that you would do if you were trying to turn this into mathematics is to just say, well, I'm going to propagate errors and see what happens, right? I've already erased it, I'm sorry. So we already sort of saw that in some sense, when you average things locally, adjacency matrices converge in some sense to a graphon, right? And so that's not true in any sort of very strict metric, but it's true in this sort of local averaging sense. And so you might hope that when you look at the Laplacian matrix, it's also going to converge to a Laplacian operator associated with a graphon. Now, that can't quite be right because things are in the wrong dimension. There are a lot more functions for the infinite dimensional thing than there are for the finite dimensional thing. So you certainly can't have anything that looks like uniform convergence, but maybe you get convergence that sort of works for most functions, right? So maybe that happens. Once you've gotten convergence for the Laplacian, maybe the eigenvectors also converge. Now that's not so obvious because you're looking for solutions to the Laplace equation, and just because the operators are similar doesn't mean the solutions are similar, but maybe that's true. And then once you've gotten convergence of the eigenvector, maybe that tells you have convergence of the ordering, right? That would be sort of nice. And if you draw a picture, it sort of looks like that should be true. If you look at the nice graphon that I wrote at the beginning, this one that I called the threshold one, the Fiedler eigenfunction looks sort of like that one. So if you have any eigenfunction that's sort of close to it, and you try to do the ordering, you can easily tell the difference between different vertices as long as they're reasonably far apart, right? So this vertex here, right, it's sort of a little bit off from where it should be, but you can tell it's certainly bigger than any of the vertices here over to the left, right? So that's something you can do if you draw this picture. On the other hand, it's definitely not something you can always do. If my eigenfunction is flat, then I can get any ordering that I feel like by having an arbitrarily small perturbation, right? If I want this point to be first, it dips down a little bit. I want this point to be last, it dips up a little bit, right? I can do sort of whatever I feel like and come up with any permutation and then just rescale it so that everything is sort of order epsilon fluctuation and get whatever I want. So the third step is actually really blatantly false some of the time, but maybe it's true for all of the examples that we care about. Okay. And that's more or less what I want to do. That sort of three-part technique is not new to me. Goes back, the first sort of long paper that's very well cited that uses it, that at least I know of, is a nice paper by von Luxburg on spectral clustering. And anyways, many people have done similar things. So I'll just say sort of for a second, what you actually do if you're running through a proof along those lines. So to get the Laplacian to converge in an appropriate sense, really the hard part is coming up with the definition, which I didn't have to do. Once you have the right definition, it's really just Hawking's inequality, so life is easy. Getting the eigenvectors to converge once you have a convergence of the matrices, that's actually genuinely hard, but I'm very lucky that somebody very clever came up with an answer to it many years ago. So there's something called the Davis-Cohen inequality and many variants of it, which let you do that. And then finally, to get the ordering, well, if you get the calculations right, that's just sort of a long calculation in Hawking's inequality again. But for all of these things to work, you need to assume something about W. To get the Laplacian to converge, life is pretty easy. If W is sort of not very spiky and is not too sparse, not too close to zero, that's just going to happen. To use the Davis-Cohen inequality, what you need essentially is that the eigenspaces are reasonably well separated. Again, it turns out that's actually not so hard to sort of get sufficient conditions for. And then this last one, in order to get the ordering to work out, you need to know that your ephemeral eigenfunction sort of looks like this and doesn't look like that one. And that one, when we started working on it, just seemed like a big mystery. So what did people do? Well, the first paper on the subject just said, well, I'm just going to work on one model where I can explicitly diagonalize everything. Okay, so that's an answer, right? If you get exactly one matrix W, you can find your ephemeral eigenfunction and you can draw it and it looks like this, and that step looks easy. And that's more or less what they do. They follow essentially the proof sketch that I had before, but for one very explicit example. When we tried to generalize this to work for sort of more or less all W, we ran into this trouble, which was trying to figure out what happened to the eigenfunction. And so that ended up being sort of the key condition. For a while, we tried to prove that that was always true for Robinson graphons, but it turns out actually it's false. There are a whole bunch of counterexamples where this doesn't work. And so somehow most of the work ended up coming up with easily verifiable conditions, which hold for all of our sort of favorite examples, even if they don't hold sort of the worst case, very strange looking W's. Okay, so that was sort of the work in this paper, was figuring out how to make that happen. And after all of that, we end up with a result that's pretty similar to the previous result, except that our constant gets a little bit worse, n to the minus 1/6 instead of n to the minus 1/5. Okay, so that's it. So in the end, things worked sort of more or less the way that we expected to. There was one bit of a surprise in that actually sometimes this algorithm actually fails, but we could check that it worked for sort of all of the models that were actually in use. So that seems sort of good enough for us. The next thing that I want to talk about is how do you clean this up? So the spectral algorithm gets you an answer. It doesn't give you sort of a very good answer. So how do you get something that looks sort of right? And okay, the details, unfortunately, are fairly terrible. So I'm going to brush almost everything under the table and just say sort of the one critical picture and say the rest of the paper is more or less doing case-by-case analysis to figure out how to draw sort of the picture for every case that you're in. It's boring and not something that one can talk about in sort of a reasonable amount of time. So here's sort of the big picture example in the nicest possible situation about how to take an ordering and make it better. Okay, so what you start with is you look at a subset of all of the vertices S, and you come up with some sort of reasonably good ordering sigma hat just for those vertices. So where can that come from? Well, we just proved consistency of spectral clustering, so we can use the spectral method. Okay, we come up with some ordering for a bunch of the vertices. And then what we want to do is we want to look at all of the new vertices and come up with a better estimate for all of those new vertices. And how are we going to do that? Well, let's imagine that I have two vertices U and V, and let's imagine that God tells me that U and V are both to the left of 0.5. And let's also imagine that I'm in the situation where W is bounded away from 0, So you have somebody who's going all the way to the right-hand end of the interval. You have some edges all the way over there. Okay. When that doesn't happen, we can deal with other cases, but this is the easiest case to draw. Okay. And all that you want to do is you notice in that situation that because of the Robinson property tells you exactly that the expected number of neighbors of V in this interval is bigger than the expected number of neighbors of U in that interval. Right? That's exactly what the Robinson property says, is things that are closer have more neighbors. At least as long as all of these sort of things are ordered in the correct way. That is, U is to the left of V is to the left of 0.5 is to the left of this right region. And it turns out that actually, even though sigma hat isn't correct, it's going to be correct enough that you can figure out that you're in this case. And it's correct enough that even though you don't get exactly the right region, the correct region for R, you do get only points that are way to the right of 0.5, which is all that one really needs for this whole thing to go through. Okay, so you can compare U and V with reasonable accuracy just by comparing how many neighbors they have in that point here. So you do that for all of these pairs, and you write down this new embedding function, which is just essentially taking the average of all of those comparisons. And it turns out that when you take this average, you're looking at essentially independent collections of edges. So you have a whole lot of cancellation. You can use standard concentration inequalities to tell you that phi hat is pretty good, as long as U and V are reasonably well separated. And so it turns out it doesn't matter really how good your initial estimator sigma hat is. As long as it's consistent, you get down to a root n error after one step of this algorithm. Okay, so that's sort of nice. You look at this sort of very coarse thing and you can improve it very, very quickly. Okay, cool, so that works. What are the S's that you use? In the second paper with the mean life was good, we thought about this for a little while. S was sort of a third or so of the graphs. We use spectral methods. In the paper with Danette, we hadn't figured out the spectral stuff yet. So it's sort of a nightmare. Anyways, I wrote down some of the details, but there are very, very, very many of these little sets, which we merge together in a sort of complicated way. In particular, what we end up doing is looking at the square. And it turns out if you do that many, many, many times, you get a whole bunch of actually exactly Robinson graphs. So you can use sort of the old computer science guarantees to make things work there and then merge things together. So this is what we do in that paper, but it's not probably actually a good idea to do that. It's quite messy, and this is probably more or less the right thing to do. Okay, great. So we end up with, well, like I said, in the end we get an algorithm which isn't so bad to implement, which gets sort of the expected error for a pretty wide class of graphons. Okay. Now I'm going to talk about sort of the two more surprising ones. So first of all, that latent position estimators don't get sort of the right answer, and then that we can do something that's actually better. I felt a need to write down this slide just for a little bit of a caveat, but I'm not going to spend very much time on it. What this slide is saying in sort of slightly messy notation is the following. Let's say that I have some algorithm which is going to go from graphs to estimated latent positions. Okay. For any given graphon W, there are a bunch of graphons that are very, very, very close to W, for which that algorithm does badly. So in other words, if you fix an algorithm, it might work for one W. I couldn't rule that out, but it's not going to work for very many W's. Okay. Sorry, if somebody wants to help me with that, I would love to. I'm pretty sure it doesn't work for any W's. But anyways, all that we could prove was that it doesn't work for very many W's. Okay. I just wanted to have that little caveat there, but with that out of the way, yeah, basically the embeddings are not very good. And then the last thing that I want to talk about is how do we go from the sort of root 1 over root n error, which is what you'd expect, to something that looks a little bit more like 1 over n error. And this is sort of my favorite idea, but also maybe hard to digest at the very end of the talk. So I'll try to go through it. The idea is just like for the voting algorithm, I'm going to start off with some approximate embedding sigma hat of some collection of vertices S. Okay. And then imagine that I'm just here in just the threshold model. That is this model here, where all of the values of the W are either A or 0. Okay, it works for other things as well, but this is the case that I'm thinking about. And I'm going to look at my two vertices U and V. And just like for the voting model, I'm going to try to compare them. So far, everything's exactly the same as the voting model. I have an approximate embedding. I have a pair U and V that I want to compare to try to sort of improve how things are going. But the details of what I'm doing are going to be a little bit different. When I was doing the original voting, The way that I compared U and V was I looked at the vertices, at their neighbors, way over to the right, as far to the right as you could go. And I looked at a lot of them. I looked at 1% of the vertices, right? Sort of a constant fraction. Here I'm going to do something a little bit different. Instead of going all the way to the right, I'm going to go, well, to the rightmost vertex that has some neighbor for U and V. So I'm going to look at a neighborhood that's special to U and V. It's not going to be the same neighborhood for all of the pairs. And I'm going to look not at 1% of the vertices, but just some small distance I of UV backwards. Okay, so this interval is much smaller than 1%. Okay, it looks big because it's hard to draw that, but this is a very, very small interval that I'm looking at here. How big does I of UV have to be? Well, it has to be bigger than U minus V, otherwise I can't really see anything. And it has to be bigger than the error in sigma s. Why does it have to be bigger than the error in sigma s? Basically so that I can tell the difference between the rightmost edge and the leftmost edge here. If I can't do that, then I'm just in trouble. And as long as I've satisfied those two conditions, then actually I can draw this picture and I can actually figure out the vertices that are in each part of those picture. Okay, so as long as those conditions are satisfied, I can actually, this picture is actually correct. Okay, I can guarantee that. Great. So now that I've sort of at least asserted that the picture is right, that I can actually do this computation, what is this doing in terms of the statistics? Well, there are two chunks of I U of V that I'm comparing. One of them, this blue region that I've called noise. Well, I know that the expected number of neighbors of V is bigger than the expected number of neighbors of U by the Robinson property, but maybe the expected value difference isn't very big. So I'm just going to treat this as if the expected value of the difference is 0, and it has some fluctuations of size roughly the square root of the size of the interval. But over here, because I'm dealing with a threshold model, if I have any neighbors here, they're all just neighbors of V. I can't have any neighbors of U. So I have a sort of a noise region, a signal region, where I'm getting always the right answer for everything that happens. Now, I don't know which vertices are in signal or which are noise, but I do know that I looks like this, and I know the size of the signal region. And the thing that's nice, of course, is that the size of the signal goes linearly in the width of this interval, but the size of the noise goes only like the square root of the length of this interval. And so as long as I can make I pretty small, I can actually improve the error. And if you go through the algebra and Hawking's inequality and whatever, what you end up getting is the following, that the comparison is good as long as the distance between U and V is bigger than the square root of this ratio here. So what effectively that means is whatever my error was for sort of sigma hat s, I can take the square root of that error. Okay, I can take the square root of that error. And even if the error is quite small, I can still take the square root of that error. So how does this turn into an algorithm? You start off with a very, very small s with a very, very bad estimate. You make another s which is a little bit bigger, and you improve the error. You make an s which is a little bit bigger, and you improve the error, and you keep on going, improving the error every time and growing the size of your subset until you've gotten your whole graph, and you've gotten an error that looks like roughly n to the minus 1. Okay, and that all terminates in only log n steps or so you can actually do it. Okay. So that's it. That's the work. Maybe I'll take this on in case anybody is brave enough to ask sort of real-time questions about something a little bit complicated. But otherwise, I'll just sort of go on to the open questions. Yeah. Yeah, this is only one step of the iterative thing. So I'm going only from S to the next. Yeah, so this I've sort of implicitly said, sorry, that I'm doing this comparison for every vertex. But actually, I'm only doing this comparison for some superset T of S, but not everything. And I keep on going. Maybe I should have said S1 and S2. Okay, so that's what we worked on. And like I said, when I'm coming to talk, I find it sort of fun to try to get people interested in problems. Despite the fact that algorithms are always a little bit complicated to say very quickly, this stuff isn't really sort of super technical. A lot of these questions are ones that people can jump in on fairly easily. So I think sort of the natural first collection of questions are, what's the right answer? So for the spectral method, right, we get this answer that looks like n to the minus 0.16. Is that really the right answer or not? I really don't know. If you do it by simulation, the cleanup step does certainly make things look a whole lot better. So spectral method is probably not the best thing to do, but we don't know what the real answer is. There are a lot of graphons for which the limiting eigenfunction phi changes sign. So there's a question, what should you do for those? There is some underlying latent thing that you can in principle recover, but nothing that looks like a spectral method seems to work very well for that. That's closely related to another question that I think is sort of natural for people who've worked with spectral things before. It turns out that there are lots of things that people call graph Laplacians which are different, and they all have different Fiedler eigenfunctions. And so there's sort of a question, you know, was I using the wrong Laplacian there? I used one that was easy to analyze, but maybe actually it makes the problem much worse. As far as I know, basically open. And then the last thing is, here was this sort of algorithm here, a little messy. I do this iterative thing. Does one really need to do that? Almost certainly the answer is no, but we don't know a really clean way to avoid doing a bunch of work here. Another collection of open questions, these ones actually I think are mostly pretty easy, but I haven't gotten around to them yet, is this seriation problem that I was talking about gets used directly for data analysis, but it actually gets used as sort of a middle step for a whole lot of other algorithms as well. So there's sort of a nice paper in Annals of Statistics which says that if you could do the seriation problem, then you would get optimal estimation of sort of graphons. But at that point, as far as anybody knew, the seriation problem was sort of NP complete or whatever, so you couldn't actually do it. But okay, now we have this, you can actually do that part of the algorithm and you can run the rest of that paper, which is sort of nice. And there are a bunch of other testing problems related to graphons and so on, which are quite closely related to this. And some questions like posterior sampling that get into MCMC, which are not as tightly related, but where this can sort of be run as an inner loop or pre-processing. And then the last question, which is really sort of wide open, I just wanted to mention these in case this is sort of interest, is these sorts of graphon embedding type problems really live in sort of a family of other very closely related problems where you're also looking at something that looks like one graph, or for vertex nomination, maybe 3 graphs. You often do something that looks sort of like taking a bunch of the spectrum and embedding things and then trying to come up with an order. And so it's sort of interesting to me, are there any of these situations where basically the same sort of tricks can do much better than spectral methods? My guess is yes. For some of them, probably it's not so bad. For some of them, it's probably a little bit messy. But there's quite a large range of problems which are sort of look quite similar, but where the mathematics is different enough that they don't all follow immediately. Okay? We have a paper coming out very soon for one of them, the Bradley-Terry ranking model, but all of these other ones are basically still just sort of floating there. So that's it. Thanks very much.
Thanks, Aaron, for the wonderful talk. I'm going to open this up to the audience now for questions. Are there any questions for Aaron?
So is there a natural extension of this to weighted graphs?
Yes, I think so. So you'd have to, I think, write down what you wanted the Robinson property to be. But I don't think that would be too bad to do. And then the rest of it, I think, should more or less work out. I think you'd have sort of the same problem, that is, is the Fiedler eigenfunction actually monotone? But beyond that, weighting is not, as far as I know, a big problem.
So, I don't know for graphons, if the graphon is low rank, you think that the spectral method can be better?
If the graphon is low rank, right. If the graphon is low rank, you shouldn't do the things that I did, but there are other spectral methods which you should choose instead. So there aren't. Okay, sorry. So I'm going to say something which might be false, but okay, if you're interested, we can try to come up with the right statement. I think there probably aren't that many low-rank Robinsonian graphons. I think that they all look, there aren't that many low-rank graphons, and most of them are Robinsonian. And so there are a lot of really nice papers which deal with estimation of low-rank graphons. And they are often cleaner if you make that assumption. So that is, in particular, when you're looking at low rank things, the Fiedler eigenfunction looks like a step function. So you literally can't distinguish between these guys, and these guys are trivial to distinguish. And so usually in that sort of situation, if you do with the asymptotics that I'm interested in, you should expect to actually get perfect recovery. So the properties are really different. And usually you can do something that's much easier. Now, I don't want to commit on exactly what technical assumptions I'm making for that to be true, but that's true for a lot of them.
Graph or a dense graph or sparse graph?
Yeah, so these are all dense, the ones that I wrote down. In my paper with a mean, we wrote down things, I always forget the name, they're like graph X's or something. Anyways, the paper with a mean, we actually don't assume density. We do a slight generalization where they're allowed to be sparse. So everything goes through, and we actually went through it all for that paper. The paper with the net, we only sort of noticed we should have done that once the thing was written, and we didn't. But yeah, there's no issue.
Yeah, so I understood that we are trying to estimate this sigma, the ordering, and maybe you told this and I missed it. So how we are estimating sigma helped us with the pottery problem, like how is this connected?
Yeah, so that was the thing that he was trying to do. So that is, he had a bunch of different types of pots, and he wanted to know which one was first, which one was second, third, fourth, and fifth. So.
So those were the graves, right?
Yes, you're right. Sorry, I was lying. Thank you. Yes. Yeah, that's right. So what you end up getting is a collection of graves where all of these things overlap. That's true. And in fact, you can easily write down a situation where one pot has a short interval and another pot has a long interval that contains the first one. Yes, that can happen, and in which case, I think the problem is not particularly well defined. That's right. If I was doing pots, I should have been doing the dual problem. And if I'm doing the graves, that's what I'm getting here. Thanks.
But the Robinsonian assumption required in order to answer the previous intent?
Yeah, so if you drop the Robinson, so I'm going to have to look at the combinatorics to think about, to sort of check this carefully. But if you drop the Robinson property, it sort of becomes unclear what you mean by the latent positioning. So what do I mean by that? Right. So when I do the W thing, I'm putting all of my UIs in a row. So it looks like there's a latent position there, right, where everything's in a row. There's nothing special about that, right? My W could have been from sort of some space x squared to 0, 1. And I can write down an equivalent graph on where instead I'm sampling uniformly on some weird space here where this thing isn't a line, right? And so in general, there's no reason to think that when you look at a graph from this, that you can put the points in a line in any way that means anything, right? You can do it, it's just, you can't recover anything from it. The Robinson property is sort of the softest thing that we can imagine where it makes sense to put things in a line. Does that make some sense? So I didn't do this, but there were some earlier papers before I got involved in the statistics where combinatorics people started sort of working on that and talking about these sorts of equivalent definitions. But that's more or less what goes wrong. I'm sort of cheating with the notation, not taking X to be some generic space.
Are there any other questions? Well, if not, let's hang around again.